So we are set. So, okay, so the title of the talk is Insight into Bubbly Flows, and I will be particularly concentrating on scale by scale transfers. And if you would have seen for the past 6-7 years, actually, if you have come for my talk, the title always remains the same, but the story keeps on changing. All right, so it's a problem which indeed I've been working for quite some time, and every time I work on it, I realize that, oh, in previous work, there's something which I missed on, and then we gain some new insights. And that's what I would like to share with you. And this. And so at least for today's talk, if you don't like bubbly flows, you could even think of the title as Insights into Variable Density Flows. And why worry about variable density flows, no matter whether you're doing plasma physics, astrophysics, or something else, is because they are everywhere, right? You could have supernovae, and I found a very interesting paper on bubbly stars. Okay, and these are giant supernovae which have, actually they have a video which looks like bubbles just coming out of the supernovae. Not supernovae, red giant star. I don't know about the physics of it, so if you want to look at it, you can look at this recent Nature paper. Then of course there are famous Rayleigh-Taylor and Kelvin-Helmholtz instabilities. And what I will be concentrating on is a much simpler system, which is bubbles rising through a fluid, which is abundant everywhere, right? Next time you look at an aquarium, think of me and think of what a nice problem I'm working on, right? So, and of course, I'm not doing all this by myself. A lot of what I'm going to be talking about is work done by Hriday, who is in the audience here. And he has also a poster, which is some recent work which he has done on machine learning in these kind of systems. And I'll try to touch a bit of it. But what I'll be primarily talking about would be works which are published here and here. So for details, you can look at this. And so let's go ahead and let's see what is the question. So the question is very simple. The work which I did was motivated by experiments, mostly done earlier in the group of Detlef Loze 20, where there were a very simple system, a large tank, through which bubbles are rising. And as bubbles rise, they generate flows. And they would like to understand what kind of mixing and turbulence is generated in such a system. All right. And this is slightly different from conventional turbulence, because when you think of conventional turbulence, you typically think of a large scale stirring, right? And then some energy would be transferred across scales through some nonlinear mechanism. And then it gets dissipated. Whereas here you have moving obstacles, which are rising because of buoyancy. And as they rise, they generate wakes. And these wakes then interact with each other and generate some kind of a chaotic flow. Whether this flow is turbulent or not, we will see. All right, but these were the first set of experiments which people did. More recently, people in Duke's and Johns Hopkins all have been looking at it. Also for the following reason, that these flows are extremely common, even in industrial settings, right? If you want to mix any gas phase into a liquid, you would do it more often than not in a bubbly flow kind of a setting. And apparently in nuclear reactors also you have bubbles which rise because of Cherenkov radiations. But anyways, I won't go into that. So how do we look at these systems? So we look at these systems mostly through numerical techniques. Our numerical techniques are way more simpler than that have been discussed in previous talks, which makes it much more amicable to analysis as well as slightly moderate size numerical simulations. So if you think about it, you have air-water system. So what describes the momentum? That's the Navier-Stokes equation. And remember, air and water have a density contrast. So that's plugged in over here. So your density is a function of the composition. And so indeed, the viscosity is also a function of the composition. The viscosity and density, we model it to vary as a linear superposition, right? I mean, it's just a linear interpolation between two phases. However, do note that if you are really thinking of a real liquid, which is what we will try to do, an air-water system, then the density contrast is huge, right? And it changes very quickly, right? So although this looks a very simple system, which is incompressible also, the variation in density is really like a shock. Okay, so you could, if you were thinking in terms of a astrophysical setting or even a compressible turbulence setting, you could think of it as bubbles of high density, which is moving through a ambient liquid and doing something interesting. And as a fluid dynamics person, when you look at all these equations, the first thing you would like to understand is that what are the non-dimensional numbers and whether we could do anything in the physically relevant regime. So the numbers are Reynolds, which is the common number, right? The Atwood number, which is the density contrast. The Bond number, which tells you how much deformed the bubble is going to be. It's the ratio of the buoyancy force to the surface tension. This is the rise velocity, and of course you have viscosity contrast, which you can also look at. It's extremely difficult to do the realistic Atwood number. A realistic Atwood number for an air-water system is 0.999999. That's very, very difficult to do. It makes the system very stiff. So as any person, right, I would like to ask that, are my results going to depend on the density contrast, right? At least the statistical properties. The Reynolds number, it looks like we can attain what the experiments can do. The Bond number looks like we can attain what the experiments can do. Viscosity contrast, not so much. But again, the deal would be the following, that A, can I reproduce what experiments do? But that's not what we are here for, right? We would like to understand that whatever experiments are predicting, whether we can give an explanation for that. And even more so, can we tell experimentalists to go and look in some area and they find something new? That would be a dream come true, right? So that's what we did at some level. And when I say we, it's people like Vikash, Hriday, and others who did all these impressive simulations of, so here is a typical simulation of bubble rising through a liquid and churning the flow as it's moving through the liquid, and the wakes are interacting with each other to generate something like turbulence. What is good is that the kind of flow structures we get and the bubble shapes we get are similar to what are observed in the experiments. And therefore, not so surprisingly, what we found was that if one looks at the power spectrum of the velocity, although it's written E here, E was meant for energy spectrum, I'm intentionally now calling it as a power spectrum of velocity, and it will become clear slightly later why. You see that for a fixed density contrast, Galilei is like the Reynolds number. As you go on increasing the Reynolds number, it looks like the power law is getting less shallower, less steeper, and you see something like k raised to minus 3. And indeed, if you look at experiments, what they found, so here is the experimental data in orange, and the blue are our simulations. They also observed something like minus 3 slope, and they called it pseudo turbulence. All right. Now, when we were doing these simulations, we first did at low Atwood numbers because that's easy to do numerically. But immediately an obvious question was, will you see it in the air-water system or not? So Vikash then went on to do simulations at Atwood 0.99. And then there were other people who did simulations at Atwood 0.999, I mean 3 nines. And then there were experiments of Rebu, which looked at things in physical space. Looks like there is a range where everyone seems to see a k raised to minus 3 scaling. And why that scaling is appearing is one of the things that I'll come to later, but not now. But needless to say, at least for moderate Galilei number, one seems to get some consistent results in simulations. Experiments seems to suggest that there is something which is agreement with simulations. All right, and so once we had that, we asked the question that, all right, if we can do Galilei less than 1000, why can't we do Galilei greater than 1000? Of course, we can do simulations. And once you do simulations, you get something that as the Galilei or the Reynolds is increasing, as expected, things are becoming more and more turbulent. The wakes are becoming themselves fairly intense. And then the question is, what do you expect over here? Do you expect something like Kolmogorov scaling to appear? Or you expect something where you don't have Kolmogorov scaling, you have minus k raised to minus 3, which is even stronger and more robust. If you again make the power spectrum of velocity and you look at it over, you do many simulations at different Galilei, and like old times when one didn't have enough computational power, what one would do is do simulations at various Reynolds number, rescale the x-axis by the Kolmogorov scale, and put all the data on top of each other. You get a slightly broader range which goes over at least 2 or 3 decades. You get half a decade of minus 5/3 like scaling. and also something which resembles the pseudo-turbulence which I talked to you earlier. So now that's interesting, because we all of a sudden find that in these simple bubbly flows, you can get a Kolmogorov scaling, which goes like k raised to minus 5/3. What scales are we getting this Kolmogorov scaling? So the place where the scaling starts is roughly the bubble diameter. One can define a dissipation scale-like quantity, which is nothing but viscosity cubed divided by the energy injected because of buoyancy to the power 1/4, which would be over here. At that crossover, you again start to see something which is decaying much less steeper than the standard viscous dissipation. Here, just for indication, I put in a -3 scaling, right? So it looks like that there is an emergence of Kolmogorov scaling. And when we first observed it and put it up, we thought that this would be never observed in experiments, okay? Because you require bubbles to be large enough, they have to deform enough and churn the fluid to observe, to attain large enough Galilei number as a collective behavior to get this physics, but we were wrong. And there were indeed experimentalists at Johns Hopkins who were able to reproduce this behavior. So in their case, the bubble diameter is here. The physical space is what you have to look at. They don't resolve much smaller scales, but you start to observe a 2/3 scaling in physical space, which indicates a minus 5/3 scaling in momentum or Fourier space, right? So that's quite cool, because whatever we proposed using our numerical simulations, it looks like that in experiments you can observe it. And what's nice is that since these experiments, there are many more experiments which have reproduced these results. And now it's fairly well established that even in these bubbly flows at sufficiently large Galilei number, and irrespective, by the way, of density contrast, you would start to observe a Kolmogorov scaling. Now that's very nice. And it looks like that it's a good time to stop for us, at least for me, and look at some other problems. But then I start to ask the following question. How is kinetic energy in this system transferred across different scales, right? I mean, if you think about it, if you think of the standard homogeneous isotropic turbulence, the way you think about it is that you inject energy at large scales. Then you have U dot grad U nonlinearity, which transfers energy through intermediate scales, maintaining a constant energy flux. And then at smaller scales, it gets dissipated, right? Now, you could do this either using Karman-Hoarth-Monin relations, which are maybe, So this is the general cartoon, right? You inject energy at large scales. This is a Richardson picture where the eddies keeps on breaking in a similar way to maintain a constant energy flux until at smallest scale it gets dissipated. And you get a beautiful 5/3 scaling as a consequence of that. And you can also then derive the exact result, which is that third order correlator would go as, or third order structure function would go as -4/5 epsilon L, where L is a separation between 2 points which you use to measure the velocity. So if you like, delta L of U is nothing but U of x plus R minus U of x. Okay. And what they're calculating, at least in this, when they say cube, is nothing but, let me call it L dot with L unit vector, and you raise it to cube and then do a spatial averaging. Okay, so that's what they do. And there Kolmogorov was able to show the exact relation that delta U cube goes as -4/5 epsilon L. And the question now is that if I told you already, right, that we saw power spectrum of velocity giving us a -5/3 scaling. So can I do an exact calculation here? Can I evaluate the third order structure function in my bubbly flow and then show you analytically that the prefactor is 4/5? That would be wonderful, right? Once we started to think about it, that's where we started to look at the literature in the variable density flow. And that was at some level my first exposure to astrophysics as well as compressible turbulence. Because, okay, we'll come back to this later, but immediately the question that I started to think was, which energy, right? For example, if you look at the compressible turbulence equations or variable density flow equation, you have mass, which is density, momentum. Let's, for simplicity, assume incompressibility del dot U. Then the kinetic energy is 1/2 rho U square, correct? Now let's take a step back to incompressible flows. How this derivation proceeds? In the incompressible flow, you are in a good shape, density is constant, so the mass conservation goes off. You have just the equation for velocity, and del dot u is 0, right? Then what you do, you define velocity increment across a scale L, derive a relation for either a 2-point correlator, which reads nothing but, so if you start from here, you do u of x, you multiply it with u of x plus or r plus L, you will get rate of change of kinetic energy up to scale L. This term corresponds to injection, this term corresponds to dissipation, and this is the nonlinear flux. All right, this is the famous Kármán-Haworth-Monin relation. You could do the same thing by looking at filtered velocities, where what you do is you take your velocity field, do a filtering operation on it. So here is a filtered velocity field. You take your velocity field, go to the momentum space, say that all the wave numbers which are greater than k, I will set them to 0. Do an inverse Fourier transform, you get a filtered velocity up to a scale k, right? From that, you can evaluate the flux, which would be equivalent of this term. You can evaluate the cumulative kinetic energy, which would be equivalent of this term. You can evaluate the cumulative dissipation, which is equivalent of this term. And you can evaluate cumulative injection, whose equivalent is this term. You can evaluate, so you take your turbulence simulation, you can either evaluate this or evaluate this. And here is a comparison. So you do the calculations either with correlations, or you do a calculations with filtered velocity, you get exactly identical results where things more or less fall on top of each other. All right. So it doesn't matter which picture you look, you get the consistent result. What is the result? Energy is injected at this scale. So wherever the flux becomes constant, wherever the injection becomes constant, that sets the scale of injection, right? So here is where energy is injected. This is the famous picture where you show that the flux is constant in the inertial range. So this is the nonlinear flux. And at much, much larger k or smaller scales, viscous dissipation becomes dominant, right? So the whole bottom line is that, all right, you get a consistent picture and you can look at it with 2-point velocity correlations, or you can look at with looking at the fluxes of filtered velocity and you get consistent picture, right? Now, let's ask the following question. If I do the same game in bubbly flows, what do I get? So let's, for simplicity, look at things with filtered velocities, right? So kinetic energy is this, but now let's say I want to define a filtered kinetic energy. I have multiple choices, and this is a problem which astrophysicists encountered quite a bit when they were trying to understand how energy transfer takes place across scales in compressible flows. You could define filtered momentum times the filtered velocity as a definition of energy at a particular scale. You can define another definition of energy at a scale as filtered density times filtered velocity times filtered velocity. You can define another thing which is square root of density times velocity filtered into itself. And then if you were from engineering literature, you could define what is called as a Favre filtered velocity, which became popular only recently by the works of Alui and Eink and Rivas, where you define a weighted momentum by the density. So it's rho u filtered divided by rho filtered. And then you define rho filtered time what is called as a Favre velocity squared. All right. And trust me, you can define many more definitions. And clearly, it's not obvious which definition to choose. Forget which definition to choose. If you pick out any one of these definitions, if I ask you, what is the equivalent Kármán-Haworth-Monin relation? Right? In the incompressible case, there was a uniqueness. You define the definition, which was unique for the filtered energy. And for that filtered energy, there was a unique definition for the 2-point correlation that you have to look at. Now, you come to compressible turbulence or variable density flows, multiple choices. Which choice should I look at? And then depending upon the choice I make, what is the corresponding correlations that I have to look at? So this is a question which actually Hriday posed to himself and did quite a wonderful job. So let me first start by asking that, okay, can I define, so how do I compare filtered quantities with their correlations? Okay, so that's what we started off with, because our idea was, if I can figure out that if I write rho u filtered dot u filtered and find out corresponding correlator, then I know what is the quantity I have to look at for which I have to make a Karman-Howarth-Monin relation. So let's try to see that first. So what Hriday first found out, which is quite impressive, is that let's say I am looking at a velocity field. So this is a snapshot of a turbulent velocity field. And if I now ask the question that if I do a filtering on it, here he has done Gaussian filtering, you could have even done a spectral filtering. The filtered field, of course, is blurred, and you get structures like this. How would I get the same field if I were looking at fields in physical space? And it's a trivial calculation that you can show that if you do an angular averaging of your field, right, you get something which resembles the filtering. Much more interestingly, what he found out was the following, that if you define p-point correlators, remember this is not 2-point, x, r1, r2, r3, all the way up to p minus 1. So if you find correlation of p quantities, right, then you can rewrite these correlators in terms of product of a filtered quantity. So you take your bare field, you do a filtering on it, you raise it to a power p, and he was able to show, when I say show with some bounds and other things, that this is equivalent to looking at a p-point correlator. The only caveat is you have to be very careful when you are evaluating this p-point correlator, because these increments are all having the same separation, right? That's how you can then define a length scale. And to check whether the ideas which we had were correct or not, he actually went ahead and evaluated the filtered field product for p is equal to 2 and p is equal to 4, which is shown in blue circles and red squares, and also evaluated the p-point correlators, and they fall on top of each other, okay, within whatever slight uncertainty. So that's quite nice, because if you know this, then you can make a table and you can say the following. Okay, the details are here, but now you can make the following claim. So if you were doing a quadratic filtered quantity, let's say rho u filtered squared, then you can define a 2-point correlator, which is square root of rho u dot square root of rho u at x plus r. If you are using filtered momentum times the filtered velocity, then you have to look at the correlators which are momentum at x, velocity x plus r, plus the symmetric part of it. If you are using rho filtered times u filtered times u filtered, then you are in a different thing. You have 3-point correlators, which is rho of x, u of x plus r, u at x plus or x plus r1, x plus r2, and all the possible permutations, right? Now you can ask, what about the Favre filtered energy, right? Because that's the most commonly used thing. If you do that, then Hriday, I won't go into all the details, but Hriday was able to show that a Karman-Howarth-Monin relation, so don't read this, this is just to tell you that things are there, but the Karman-Howarth-Monin relation for a Favre filtered energy would require multi-point correlators, right? I already told you that there are definitions which would require 3-point correlators. Here you would have series which would require multi-point correlators, and then we are in a fix at some level when we think of it in terms of the theory of homogeneous and isotropic turbulence. When I learned homogeneous isotropic turbulence for incompressible fluids, one thinks of homogeneity and isotropy in terms of the 2-point quantities, right? Now, if I have to look at, or if I'm looking at a Favre filtered quantity, then what do I mean by homogeneity? Clearly, that means that I have to think of homogeneity for multi-point correlators in physical space, right? Or if I was using this other definition, the rho filtered, u filtered, u filtered, right? Oops. So for example, a quantity like this, rho filtered, u filtered, u filtered. Then I have to look at 3-point correlators, rho of x, u of x plus r1, u of x plus r2, and indeed the two agree with each other. But then again, the question is that when you have to interpret your results in terms of homogeneity and isotropy, you have to be extremely careful. You have to do averagings and other things in a proper way to figure out that is the system really homogeneous or not, at least for these variable density flows, right? So with that, let's go ahead and let's take the case of the real system. So the reason I pointed this out to you was because I wanted to emphasize that it's not a very obvious thing to derive the Karman-Hoerth-Monin relation and then say that, oh, in bubbly flows, it's very obvious that you will get 4/5 epsilon r, right? Naively, one would have thought that, look, there is a Karman-Hoerth-Monin relation, there is an exact relation there. You observe 5/3 scaling, and so it's obvious that you should have constancy of flux. It's obvious you have a, that's not obvious at all. All right, that's extremely non-trivial once you have a variable density flow. Actually, I'm not aware of if there is a corresponding exact result in the variable density flow for the 4/5 law. All right, and one of the things which we did at some level was take these two different definitions and ask, if I look at the energy transfers in these bubbly flows, do we get the same picture or not? All right, and the reason I'm pointing it out to you is the following, that we don't get the same picture. Okay, so on the left is momentum times velocity picture, where what you find is something interesting. So first is, here is an injection, and you see injection goes higher than the largest value it can or than the value it attains at largest scale, which means naively, if you were thinking on terms of energy fluxes, you would say, hey, there is a mechanism by which injection itself at some intermediate scale is injecting more energy into the system than what it could inject if there was no filtering. That sounds funny. Furthermore, we found something which was even more crazier, was that if you look at the pressure term, remember this is a variable density flow, so pressure can also transfer energy. The pressure term was changing sign, which means that within the momentum velocity picture, you would say that the pressure is injecting energy at some scales or transferring energy upscale at some scales and downscales at some other scale. The viscous dissipation is what you expect. The surface tension tells you that. So if you look at the surface tension term, that's this F sigma. It tells you that at some scales, it's injecting energy into the system, or it's taking in energy from the system because from injection, and other scale, it's putting it down at two smaller scales. So that picture is all right. But there is a somehow very contradiction between the buoyancy injection and the pressure term. The same thing if you do in Favre, you get a much cleaner picture. Buoyancy is now injecting energy at all scales. There is no something where it injects more energy than what it could do in the total system. Dissipation is consistent, of course. The pressure now always does a transfer upscale. So this is the pressure transfer. It doesn't have this ambiguity that at some scales it's transferring energy downscale, some scale it's transferring energy upscale. The nonlinear term transfers energy downscale as expected, and I already told you how the surface tension behaves. Now that's quite remarkable, because that means that if you, depending upon the choice you would have made, you would have given a completely different physical interpretation of the underlying dynamics, right? We were able to conclude, at least for our system, that the Favre filtered framework is better because it consistently predicts that buoyancy only injects energy at all scale, right? So our logic of making a choice was based on what physics we think is correct, right? But that need not be case for everything that one looks at. And so that's the first message, at least for this part of the talk, that you have to be careful when you're working in variable density flow. Even the choices you make could have a consequences on the physics that you interpret. So with that, I'll just go quickly, because I have, I think, only 10 minutes. So this is the first message of my talk. What I'll go to is something which is very recent, which again is done by Hriday. I'll just skim through it. The details are in the poster of Hriday, so I encourage you to have a look at it. Another problem which we started to look at in bubbly flows was the case of flow reconstruction. And the reason for that was, again, we were motivated by experiments where what people observe is that, remember, bubbles is an air-water system. So if you use optical methods, the bubbles look like shining things which are going. So you can't see what's happening inside the bubble. If you use a hot wire anemometry, then what happens is that because the conductivity of water and air is very different, you are not able to even capture signals. You get spikes. So here is a typical signal from experiments. Whenever the probe crosses bubble, you have a spike in the system. So when they, in experiments, measure any of the quantities, they do some kind of masking or some other techniques to look at what are the statistics. The question that we had was, can we use some flow reconstruction method to find what is the flow field inside the bubbles? And remember, this is a very challenging problem. The underlying flow is turbulent. Okay, you are doing a 3D flow. You can't give it just 2D slices, right? And the question is, so computationally also, if you are using any machine learning framework, to train it on this system is cumbersome. But thanks to Hriday and the group of Luca Bifrale and others, what we ended up doing was a very smart trick. We said that, look, the flow has anisotropy because bubbles are mostly going upward. So hopefully, if we just take enough number of 2D slices, use a diffusion model to learn the flow field, maybe we would be able to reconstruct what's happening inside the bubble. And that would be nice. So the question we would like to pose is the following. Let's say you do your training using diffusion model on the 2-dimensional slices of the flow. Then what you do is you mask whatever is happening inside the bubble. So you don't give information of what's inside the bubble. Question is, if I go give you flow outside, would you be able to reconstruct the flow inside the bubble? And remember, that's a very, very difficult question. Why? Because the density of contrast outside and inside is different. Therefore, the flow statistics outside and inside is very different, right? So if I just give you the flow outside, asking you what is the flow inside is very challenging. All right. So we undertook that challenge, and what we did was we used diffusion models. I won't go into the details, but this is a standard framework that we used. We first take a snapshot, add noise onto it until it completely becomes, featureless. And then you have to train whatever is the hyperparameter so that if you go inverse, you get back the same framework, same picture. And this is what we ended up doing. I don't have time, so I won't go into the details, but suffices to say that our data set is the following, that you have periodic DNS, 512 cube resolution, training data set is 7,500 vertical slices, plus phase shifts to make fairly large data set. For validation, we again have 4,000 independent slices. And for reconstruction and testing, we do further independent runs. So, when you are going to do reconstruction, you would take independent slices and then do reconstruction with them. We downsize the data because this itself was cumbersome. And the training takes some time. I mean, 4 days on 4 800s running continuously. And this is only for 2D slices. And DNS is roughly 2 months on 64 GPUs. And then what you get is the following. So you can do the 2D reconstruction. So let's say you start from noise, you would see all of a sudden bubbles start to appear, and then there is some wake of it. And if you look at the vertical velocity profile, you aren't able to distinguish between whatever is generated from the diffusion model, and the circles are the DNS data. And similarly, this is vertical velocity inside the bubble, and this is the vertical velocity in the liquid. The two agree fairly well. Now we are going to do a more difficult thing. To our model, we are not going to supply this information, whatever is inside the bubble. We are going to push it such that the velocity field outside matches whatever is given to it. So I'm going to give it a velocity field of the outside fluid, push the model such that it mimics the velocity field outside, and see whether whatever I get inside is consistent with whatever is expected. And so this is the idea of this posterior sampling, that all these are places where bubble was. You hide this information. You have already trained your machine learning framework. And now you ask the question whether if you rerun the machine learning framework, but with a penalty that it pushes the outside velocity to whatever it was earlier, or which is given to it, then what you reconstruct inside. And here is a reconstruction where you see that the machine learning framework is able to reconstruct the flow inside, which is quite nice, because that means that if to experiment running at the same Galilei number, if they give me just the flow field outside, I can tell them what is happening inside the bubble. Even more interestingly, what Hriday did was the following. He said that, look, we only, that thing doesn't come in, but okay. What I think is there in the poster, what we can also do is to generate the 3-dimensional flow field from the 2D slices, where we are able to get the full 3D flow inside the bubble. And that's also quite nice, because then it's like a MRI, where you can generate the 3D flow structures just if you provide it sufficient number of 2D cuts. So with that, I will stop. And if there are any questions, I'll be happy to address. Thanks. Yes. Oh, yes. Yes. So 2D flow size slices of the flow outside, which is okay because 2D PIV is fairly good in these. I mean, at least the Johns Hopkins and other groups which have sufficiently sophisticated cameras and other things, they give you the full 2D slice. So by the way, this is the 3D flow reconstruction. This is the ground truth. This is the reconstructed 3D. Don't have it. I mean, we have proposed it to the experimentalists. Let's see how it goes. No, so the idea would be the following, and that's where it's fun. That at the same Galilei number, because the energy spectra and other things and the bubble shapes are matching, what we would be doing is we will training the machine learning on our thing. Experiments could do it at different Galilei, and then one can compare the two. So the ground truth can be compared even at low Galilei numbers to begin with, where they have some idea of what is flow inside the bubble. So
Prasad, very interesting talk. I wanted to know this bubbles.
Yes.
You originally keep them or they keep forming and...
No, so we start with bubbles.
You start with a fixed number of bubbles.
Yes.
But can you have simulations where you have two fluids, let's say air and the water, and then you have surface waves, and if the waves break and entrain bubbles and those kind of simulations
those simulations are fairly difficult in the sense that you could do those simulations in the sense that numerically and other things, but evaluating all these quantities.
No, I don't want to evaluate this, but just at what amplitude there is wave breaking, how much of energy goes to bubble and all those things.
So pictorially, you can get many of the things which look okay. The challenging thing is, can you get quantitatively things precise, which is where it becomes tricky, because you see the breakup of the bubble is a very difficult problem. So you see, if you would, so there are different methods. One of them is like phase field method, which has all the physics inside it, but that has a fairly diffused interface, so it over predicts breakup. Then there are other methods which are used like volume of fluid in the or level set, where breakup is a surgery, right? So it's doing it very consistently is very difficult. That's why we chose a problem which is way more simpler, in the sense that bubbles only deform so much, and there is no breakup of bubbles involved, there is no coalescence of bubbles involved. Otherwise, it's, you can get lots of physics correct, but if you want to compare with experiments and other things, that would turn out to be fairly difficult thing to do.
Okay, so another question at the back.
These diffusion models are good to generate visually good results. But in your case, it looks visually similar. Have you quantified it?
So I have plotted the PDFs, no?
Okay.
So we looked at even 2-point correlators,
right.
The flatness as a function of scale, the structure function, so everything, even inside the bubbles.
Okay. But are you using any kind of a constraint? Are you checking how far it kind of obeys the PDs that you are working with?
So this is free generation. So we are not putting in any constraints. So even, for example, in the reconstruction, when I do the 3D thing, right? In 2D slices, there is no incompressibility, right? But in 3D, of course, you expect the full flow through to be incompressible, right? But because it's a free generation and we are only training on 2D slices, when you go in the other direction, right? So, I mean, if you look at it carefully, the flow is not very incompressible. And that indeed, as you're rightly pointing out, could be improved by using a physics assisted thing where you say, look, I want to put another constraint that the divergence of U is 0 or some other thing, right? But we didn't do that because by itself, you see the amount of GPU times and other thing it was taking was fairly cumbersome. So one of the things which I didn't like about it at some level, if I had a GPU solver for bubbles also, so I have a fluid solver but also GPU for bubbles, then maybe time for training and reconstruction would be as good as for me to run a full DNS. And then it's not a fun exercise.
But I think that's wherein the pins would actually improve.
I don't know. I mean, this, because Luca and others who are working on this quite some time. On turbulence data, at least it looks like it doesn't give you as much improvement as one would have, at least as I would have liked. I mean, people, we are happy that we are able to do that, but it's not that, once I have learned, or the algorithm has learned the free generation, the images are generated so in a second I can't generate thousands of images. It takes good amount of time to get images which give you correct statistics.
Okay, so we can take one last question, but please be brief.
Thanks for the talk. I have two questions. Like one is,
Maybe you can ask one question which you consider more important.
I'll include in that. So the question is like, during these simulations, like it's a periodic box simulation.
Yeah.
And like, what is the distribution of the initial bubbles you are allowing in the system to kind of generate that pseudo turbulence you mentioned? And did you allow the coalescence of bubbles in the?
No. So the thing is that the volume fraction that one is working at is 2 to 3%. Why? Because experiments are done in that regime typically. And there, as in our simulations, coalescence are extremely rare or don't happen. The other thing is that in most experiments, the surface of the bubble is contaminated by dust, which again prohibits the coalescence of bubbles. So the method we choose at some level helps us or is consistent with experiment, although we don't put any dust or other thing on our bubbles, but the way it is designed, they don't coalesce. Huh? Sorry? Okay.
Okay, so let us thank Prasad again.